Okay. The addition of Br2 or Cl2 to an alkene is number 2 in your functional group notebook. The addition of the halogenation of alkenes. The general product of these reactions is that only Br2 and Cl2 halogens will react with an alkene in this way. The bromine or chlorine gas react with the alkene to add bromine to each of the vinyl carbons to make a vicinal dibromide or a vicinal dichloride. Remember that vicinal means that on adjacent pi carbons. So that each of the sp2 carbons gets one bond to the halogen. The molecule shown under the reaction arrow is only the solvent. It is completely inert and does not participate in the reaction. It is a spectator. On the exam, a lot of students try to incorporate these atoms, CH2Cl2, into the product. If you do that, you will be giving the wrong answer. Let's look at the mechanism for the addition of a halogen atom. I recommend you fill out your functional group notebook while we work on this, while we look at these slides. So what occurs on the first step of the reaction is that the pi electrons of the pi bond will form one bond to bromine. A lone pair of the bromine will bond to the other pi carbon. When that occurs, the bromine will have an octet. Therefore, the bromine to bromine bond must break, forming a bromide ion. This forms the products cyclic bromonium ion. This is called a halonium ion. You will most likely be asked about this intermediate on an exam. When bromine has two bonds, it will have a positive charge. Our bromide ion that is formed when we break the Br-Br bond will donate a lone pair to form a bond to a carbon atom. Then the CBr bond that existed to the positive bromine breaks, and we end up with one bromide ion bonded to each carbon. In this reaction, both of the carbons are equivalent. And so the product is a chiral. This will be different if we have a chiral reactant, or if we have a pi bond where the two carbons are not equally substituted. And that is why I have drawn the addition of bromine with solid and hatched wedges, because the bromine can add either above or below the pi bond. We have the potential to form more than one product. And this will result in more than one final product when we have the final solution. In addition, when the second bromide ion bonds, it can't bond on the same wedge type as the original bromine because there's only one solid wedge. It has to bond opposite of that direction, which makes the two bromines anti to one another in the product. It's very important to remember about the name of the halonium ion intermediate and what the general shape is. A three-membered ring to a halogen that has a positive charge. The carbon atoms are both connected to the bromine atom. The carbon atoms that are both connected to bromine are the most electrophilic atoms, most electrophilic carbon atoms. Bromine, of course, is the most electrophilic atoms out of all the atoms in the molecule, regardless of the positive charge. So note that in the formal drawing of the Lewis structure, bromine has a positive charge, but bromine is an electronegative. And so it draws electron density from the carbons. It does not maintain that positive charge. Instead, it takes the difference of electrons from the other atoms that it is bonded to. For this reaction, we do not go through a carbocation intermediate, so no arrangement will be possible, as a carbocation is not formed. For each of the carbon atoms, they will each get one bond to bromine, and that will give us our product. Alkenes do not add iodide in this manner, so I too will not add in this manner. What occurs in reality is that diiodide, a vicinal diiodide, is extremely unstable and will undergo spontaneous elimination of the iodide ions to form the alkene. Note the reaction arrows. The diiodide is not the favored product. Instead, the alkene is the favored product. The equilibrium is such that it is for formation of the diiodide is way less than 1. And because the equilibrium for formation of the diiodide is so small, we know that the reactants are favored. This next reaction is the formation of halohydrins. The formation of halohydrins, I believe, is reaction 3 on your F functional group notebook. In this case, we have changed solvents. Instead of the inert and unreactive CH2Cl2, we are using water as a solvent. When this occurs, we will form our halonium ion intermediate. But when we compare the basicity of bromide ion to water, you will know that water is a stronger base than bromide ion. How can we know that? Compare the conjugate acids. If it's a stronger acid, it will have a weaker base. So which is the stronger acid, HBr or H3O+? HBr is the stronger acid. Therefore, Br- is the weaker base. Because we now have a stronger base than bromide, water will act as our nucleophile instead of the bromide ion in the second step. Our water oxygen will donate a lone pair to form a bond to bromine. In the reaction shown, we have an unequally substituted pi bond. We have one side of the pi bond with no bonds to carbon, and one vicinal carbon that has one bond to carbon. So that we form actually two intermediate reactants. One where bromine adds to the bottom of the pi bond, and one where bromine adds to the top of the pi bond. Water will add in a Markovnikov. Water will add to the more substituted carbon. So in this case, the water lone pair will bond to the carbon with more bonds to carbon, and the bond between the C and the Br will break. This will give us what we call a halohydrin. A halohydrin is a molecule that has a bond to an alcohol group and a bond to a halogen group. We form two final products. The bromohydrin is a major product. We will also form as a minor product the dihalide. But for the bromohydrin, we actually have two enantiomers. The chlorohydrin reaction occurs by the same mechanism. You should fill this into your functional group notebook while you're looking at it. Let's go over this mechanism again. Bromine, the pi electrons of the alkene bond to bromine, and one of the lone pairs of bromine bonds to the other pi carbon. Because these two new bonds result in bromine having an octet, the Br to Br bond must break, producing bromide ion. On the second step of the reaction, we have our halonium ion that was formed in step 1 and our bromide ion that was formed in step 1. Now the water molecule and its lone pair will donate its lone pair to form a bond to the more substituted carbon. The carbon to bromide bond will break, and we will have a protonated alcohol group in addition to our bromine that is still connected to the less substituted carbon. The protonated alcohol will be deprotonated by another molecule of water. The molecule of water will donate its lone pair to form a bond to hydrogen. The hydrogen to oxygen bond of the protonated alcohol will break, giving us a simple alcohol. We now have our halohydrin, one alcohol group and a bromine on an adjacent carbon. The alcohol group should be on the more substituted carbon and the halogen on the less substituted carbon. How do we know that this follows the same rules that we have been observing? The electrophile adds to the sp2 carbon bonded to the most hydrogens. In this case, bromine is our electrophile. And by forming our halonium ion with the partial positive charge is on the carbon that has more bond to carbons because that is a more stable position for the positive charge. So in that transition state, the more electrophilic carbon is the more substituted carbon, and the nucleophile, water, adds to that carbon. We'll pick this up again on Tuesday with our next video.